Okay, so I think that we can start, and we are going to leave Millipede aside for the moment. We are going to uh, go back to Millipede after this brief introduction that we are going to do with Caramba 3D. As you can see, this is the toolbar for Caramba 3D. Um, if finally we have a um, let's say structural analysis software or plugins that doesn't have some kind of weird interface like Millipede. Remember from yesterday this kind of strange aesthetics for the component and also the wires, the connecting wires. We are back to normal with Caramba 3D. I was telling you yesterday a general overlook on these plugins. They all work the same. So you see that also grouping of these components inside Caramba toolbar, it's very clear. You have the model definition, loads, and then cross-section. Well, basically, they might be, let's say, in a weird order eventually, but it works absolutely the same. So you have the model, load, cross-section, and material, the algorithms, which are the solver, basically, and then the result. And some utilities, as always, with Grasshopper plugins. Okay, um, so we are going to build more or less the same structural analysis, but we are going to use Caramba 3D, which, for those of you who are interested not only in running some simulations, just to have an idea of the general behavior, structural behavior of your model, of your system, but you also want some information, some detailed information or analytical information about magnitudes and the values that you have for stresses, forces, reactions, and so on, then Caramba 3D is probably the best solution. Um, one introductory information, one preliminary information. If you don't have a full license of Caramba 3D, you have some limitations regarding the number of elements that you can use in your simulation. Um, if I'm not wrong, if when we are going to work right now with a simple truss system, which is basically a frame. So there are just linear elements. In that case, for example, Caramba 3D, the trial version only allows up to 20 or 25 elements. Okay. Um, there is also limitation regarding, for example, shell analysis. In that case, I think elements increase to 50 or something like that. But you can also Caramba 3D also has some special licenses like educational licenses and also workshop licenses actually, but I didn't manage to obtain one of them. So I don't know what's your situation, but if you see that something becomes red, some components in Caramba 3D become red, probably or most likely it's because you are exceeding the amount of elements that are allowed in the free version. Okay. I have a full version of Caramba 3D, full educational version, so I don't have this kind of limitation. If you want to double check the status of your license, you can use this license component here. And once you place it here, you can simply read the output of this component and see what type of license, when is it going to expire, and so on. So we are going to use a simple truss system in order to perform some kind of simple analysis. And I think I better start from scratch this thing because it's going to just be reading information without having the full possibility to comment and to understand fully what we're doing. In order to draw this truss system, as I was suggesting also in the course page, I will be using other plugins. There are some plugins that allow creating a truss system more or less automatically, so I will use one of them. And the first that comes to my mind is Launchbox, where you have this kind of automatic grids or 3D spatial structures components. And the first one is a two-dimensional truss. There are also space trusses, but it's just increasing the amount of elements. Actually, it doesn't change much in the study that we are going to run right now. So I'm going to take the 2D truss, which is a pretty nice component. It only asks for curve A and curve B, which are the upper curve and lower curve, or vice versa, as you want to see them. And then the amount of divisions that you want in your truss, and then what type of truss you want to create. There are also other plugins that have this kind of automatic truss creation, but in this case, we only need a simple two-dimensional truss, so this is more than enough. And curve A, curve B, I want you to pay attention to this because when Grasshopper components ask for a curve, they are not asking for a straight line. So you can also use, I don't know, well, without going into the unknown, right? So we can also use, for example, a curve or like an arc, for example, in order to have a curved truss system. But anyway, let's keep it simple, and let's start with some kind of curve, which is going to be just one simple line in Rhino. So I'm going to create a line controlling the dimension, like this is going to be 10 to 20, so 20 meters span total. And also I'm going to take this one and copy it down like this, so 5-meter height. And so I need to import, not reparameterize, sorry. I need to import the first one and the second one. And this would be curve A and curve B. And you see that automatically you already have this truss. I'm going to internalize these values because I don't want Grasshopper definition to depend on two lines in Rhino. Okay, here we are. And divisions, I'm going to use a slider, like an 11 slider. 11 slider, I don't know if you know how sliders work in Grasshopper, but there are some presets that I almost always use. So if you know that if you write down a number, then you hit enter, Grasshopper creates a number slider. So the range is going to be from 0 to the next multiple of 10 that you have after the number that you are specifying. So if I hit enter, I have 0 to 10. If I hit 11 and enter, I have 0 to 100. If I hit 101, I have 0 to 1000, and so on. So if you want a good range of number, you can simply write down the value that you want to include in your range. Just consider that the range extends to the next multiple of 10. Sorry, power of 10, actually. Okay, so 11 as the division, so we will have this kind of variable amount of elements. And the truss toggle. So truss toggle is just an integer number between 0 and 2. There are also other components that allow more truss types. So in this case, we only have 3 options. Okay, so this is the first one, this is the second one, and this is the third one, which are basically one is the opposite of the other. So the real difference is between 0 and 1. Okay, but anyway, according to the distribution of loads, eventually there will be also a difference in the performance of the truss, even between 1 and 2, of course. So this is going to be our system. So you see, it's very easy to create it, and the result is divided by type of lines, which is basically the function of your elements here. So if I isolate the output, you will see that. Let me get rid of the preview of the initial. So you see that primary lines are basically the lower and upper lines. Then there are the brace lines, which are the diagonals, and the vertical lines, of course. And there are also the nodes, which are basically the intersection points between all of these elements. Okay, so we are not going to concentrate on nodes. Eventually, you can also consider the deformation of your system, studying the displacement that you have for your nodes. Okay, so these are the nodes before the simulation, and of course we will have the nodes after the simulation. So you also can use this information, which is somehow important, to evaluate how much the structure is deforming during the simulation. But we will concentrate on these curves, actually. So let's go back to Canva 3D. So first of all, we must build the model. And it's more or less like in Millipede. Okay, so we have linear elements. So I'm going to use line to beam, for example. There are many other ways, as in Millipede, to convert linear elements or curves into structural elements. So you see also, for example, connectivity to beam, which is basically a more automatic way of creating a system of beams from a connectivity topology system in Grasshopper. But in our case, we have just a bunch of curves, so line to beam is more than enough. And we need to convert all of these elements into beams. But we can also, let's say, either we give all these elements the same properties, like connecting all the three curve containers to the line input, or we use three components like this, or actually two, well, no, three, because we have upper and lower beams, and then we have diagonal and vertical. So I think three is the best option. This is going to be a little more, a little richer as definition with respect to the original one that I did, because in the original one, I just used one single line to beam component for the three types of elements. So this is going to be somehow more detailed. And of course, I'm going to share this with you at the end of today's session. So let's create this for the upper and lower beams. This is very simple as a component. What I would do in this case is, for example, in order to apply the loads in some strategic portion of the system, we will have to detail a little the definition of this line to beam component. So we are going to use, for example, identifiers for some specific beams. We will discuss this in a while. Caramba 3D components are very rich components, very rich functions. You always see something like this black tab here that you click on it, and you have some more options inside your component. These allow to define some properties regarding the tolerances that you want Caramba to adopt when converting elements into, lines into elements, and also in other model construction components. You always have this kind of behavior inside your functions. In our case, the really important one between these options is the bending. So you see that if you allow an element to bend, it behaves like a beam. If you don't allow the element to bend, it behaves like a truss. So it is a truss element. And in our case, we must specify that the bending must be false. Okay, we don't want this element to be able to bend. We want the structure to bend in order to have this element to work only on compression or tension. Okay, so in this case, we must plug a Boolean toggle, set it to false, and plug it into bending. Once we do this, it's useless to have these components expanded. You see that the false stays connected to the options, and we already know what this option is actually adjusting as a value. Cross-section. Remember, like in Millipede, you define the element and you must define the cross-section. And so here, again, you have the cross-section. The main selector is the cross-section Caramba 3D. But there are a bunch of components that allow a more detailed construction of the cross-section of a beam, of an element. Okay. So we are going to use the simpler one, but you can also specify some very, very detailed structural parameters in your model. Okay, so and you can also use an automatic, for example, I don't know, like generate cross-section table in order to have something like a legend for the cross sections that you are using inside your model, and just to derive some technical spreadsheets for production. But in our case, we just need to define the model. So we are going to use this simple selector. We must, first of all, we must specify the general shape of the cross section. It's here at the bottom in the usual option section. You have several presets. So you have I section, you have this box hollow section, this O section, shell, and then there is something, for example, that I have used in the actual definition, which is the trapezoid, because trapezoid is the way that Caramba 3D lets you create some like solid and not hollow square or rectangular section. So like a square section bar, you must use the trapezoid cross section, okay? Because these two here are hollow section, okay? So there will be a thickness for the wall, while in this case you have a solid bar. Now it depends on how you want to simulate your elements, what type of cross section you want to use. I will stick with the trapezoid in order to detail how you must populate this parameter in order to obtain the same script that I have already created. These, for example, family name across section are just text. So you can give the right name to this element in order to have them available during and after the simulation. Okay. So it's optional, of course. There is no particular reason to name them unless you are working with some provider, specific provider that gives you a catalog of specific models. And in that case, you might want to populate these inputs with the right name and or let's say product category and product name, basically. Element identifier, it's once again, it's something that we are going to discuss in a while. And once again, you have the selection of material. So you see, it's always the same. It's like in millipede, actually. Okay, so you go into the material group, and there are some components here. There is a material properties. You can define them. It's like the what was the name in millipede? Like isotropic material, something like that. Let me find millipede. It was, yeah, isotropic material. While here in Caramba 3D, you have these material properties. You define a material from the properties that you must have, of course. And there is the material selection that we are going to use. So here it's way more simple. So you have the family of material. Steel, reinforced steel, concrete, wood, aluminum is the presets, and inside the family you can, for example, select what type of, in this case, steel, or you can select, for example, I don't know, something like wood, reinforced steel. You see that everything changes according to the family that you decide. I'm going to use a standard S235 steel. Of course, if you change this, you will have consequences during the simulation. So more or less deformations, or more or less maximum displacement, more or less weight, and so on. Okay, so this is the material. I'm going to collapse these. I'm going to define the material for these cross sections. And I'm going to define the properties, geometrical properties of these cross sections. So,
excuse me, Giancarlo.
Yeah, tell me.
What material you are using?
Well, actually, it doesn't matter. Actually, you can use whatever you want, but I'm using steel S235.
Okay, perfect.
Yeah. So, so this is eccentricity of the cross section. If you want to specify this parameter here, but we are going to work with symmetrical cross section. So we are going to make it simple, basically, in order to understand how this process works. And then you can add whatever kind of details you want to your system. And so you see that there is no thickness here because this is a solid cross section. So it's filled, and you only have height, upper width, and lower width. And as we want to work, for example, with a square section or a rectangular section, then we must leave upper width and lower width like with the same value. Okay, so let's keep it simple in order to don't have many sliders and parameters during the optimization process. So height, I would say that something like between 0. Let's say we are considering a span of 20 meters, so let's say 0.10. Oh, sorry. Just pay attention to this. If you hover with your mouse on this input, you see that height must be specified in centimeters. So that's what I was telling you yesterday. You must always double check what the input is asking for. So in this case, even if you are working in meters and Coramba 3D works with meters, actually it asks for the cross section in centimeters. So don't ask me why. It's just the developer's choice in this case. I would have kept all in meters, but just pay attention to this. Also, I'm going to write down a scribble. Check units because they are in centimeters. Okay, so pay attention to these little tricky aspects when working with these plugins. Okay, so in this case, height is going to be between what I told 10 centimeters up to maybe 40. Let's see what the optimization process suggests. You're right, Sura. My Rhino is set to millimeters. Now, in this case, I can change this on the fly. I told you yesterday, always start with a meters template before doing anything in Grasshopper. Now, this is not exactly true. Grasshopper is unitless. I want you to have some kind of workflow that avoid any type of errors. In this case, I can do it on the fly because Coramba 3D is not affected in real time. But for example, if you are working with some kind of interoperability workflow, like sending Grasshopper information to other software, in that case, this information might not be read in real time from Grasshopper. So there might be some scale problem when you import the information in other software. Okay, but in this case, thank you for this observation. Okay, so yes, basically height, and also I'm going to copy paste this. I'm not using the same sliders. I don't want necessarily a square cross section. I want it to be eventually rectangular. Okay, so like this. This is going to be the cross section for our beams. Well, actually the upper and lower beams. Okay, and then let's go to the diagonals, which is basically repeating all the process. Actually, what I'm going to do is to collapse this thing a little, and I'm going to move everything a little farther than this, like this, and I'm going to reorganize a little this this part of the definition. Can we use angle beam as cross section? What do you mean, Andre?
No, not only solid section, but angle section or T section.
Oh,
or
like C or yeah. Actually, you see that in the cross section definition, you could eventually do this. Let me double check. Of course, you can, but the matter is just finding out where you can do this. I think you can do something with these modified cross sections, or you can eventually come up with a customized cross section. Because actually, what you have here in this selection component, you only have available these types, let's say, of cross section. So in this case, you cannot do this. But of course, you can use a customized cross section. Actually, it's something that I didn't do. So I don't have the answer at the moment, but if you want, we can further discuss this later on. after the course, and I will be glad to give you the solution of this. So no problem.
Okay.
Yeah.
Okay, it will be very important. Thank you.
Yeah, it will be very important. Absolutely. This is something that eventually is leads us to a more specific and advanced use of car number 3D, which is an absolutely a very powerful tool. There are many features that we are not going to discuss during these classes, but yes, of course, I will be. It's also interesting to me to give you the solution. Okay, so yes, so. What I'm going to do, I'm going to take this, bring it here, make it wireless, so I will avoid some noisy wires inside the canvas. And what I'm going to do, I'm going to simply copy this, paste it like this, and substitute these curves with the new ones. And so, and make this wireless as well. Okay, and then we will have, let me also, well, actually, we can also group this just together at the end. So I'm going to copy paste this, grab this, plug it here, and make it wireless again. So something like this, and I'm going to select this, right click on this group and add to group in order to have all of them grouped together inside this warning here, which I can also make like a rectangle outline, so I avoid this kind of weird red areas. Okay, so now we have defined the behavior of the three beam systems, and what I'm going to do next is just give some variation to, well, no, because I want the optimization to find the right solution. So I was thinking about changing, for example, the range for the diagonal elements in order to have them a little thinner than the others, but I want the optimization process to find the best solution in terms of weight and performance optimization. So let's say these are the three elements. Each of them have has the couple of sliders that define the geometric properties. So we come up with these three elements here. Then we must define, for example, the support. You see that here, for example, loads are not contained inside the element definition, like in millipede. Of course, in millipede, you can also specify additional loads, like we saw yesterday, that there are some region loads or point loads and so on. But there is also a linear load applied to a linear element, which is something that we don't have here. Okay, so in this case, for example, loads are simply here in a separate group of component. In this case, we must use the loads, which is this component is once again, it's a dynamic component. It's one component, load component, that allows to create whatever type of load you might want to use. Okay, so in this case, I'm going to use, for example, like gravity, well, actually not gravity. I want to use a uniform line. So in order to apply this load, for example, to the upper linear elements that I have here on top. I also want to have some kind of even separation here, even divisions, in order to avoid this kind of asymmetric structure. So I'm going to tell divisions that I only want even numbers. So in order to have to always have a symmetrical truss system. So what I want to do, I want to apply this load only to the upper beams, not to the whole structure, because this is not going to be gravity. Okay, we can also define gravity. Gravity will be applied to the whole system, but you know, in this case, for our study, it will only affect the final result. In terms of, there will be an additional diffused load applied to the whole system. While what I want to do, I want to differentiate the load application and apply only to a portion of the system. So like if there was something that was lying on the upper beams, okay? And then we will be using the supports. So in this case, what I need to do is apply the load only to specific beams. And in this case, beam ID, basically, is the way that you can detect or select the beams where you want to apply this load. Now, remember that our beam or the line-to-beam component has an identifier input. Okay, so this is the name that you give to each element, and you can give whatever name you might want to your elements, but as this is an information that you can also visualize during the simulation, I would recommend that you give some representative names to the beams or to the elements. Okay, so in this case, for example, we have the primary lines, which are the upper and the lower beams. We must, first of all, we must understand how these elements are sorted inside this output here, okay, in order to detect what are the beam lying here on top and at the bottom. So if I, for example, do a quick check with a list item for the primary lines, I see that the first one is this one. So I'm already considering the upper beams. Remember that here we have all the upper and lower beams. Okay, so we have in this case 28 elements, of course, twice this amount. So if I take a slider between 0 and 27 and plug it here, keep this selected and move this slider, I see that they are alternated, up, down, up, down, up, down, up, down. Okay, so once I know this, I know that if I want to separate the beams, I can use a dispatch component. Remember that the first item of the list was an upper element. So all the upper elements are right now in list A. We can double check this, and all the upper elements should, yeah, exactly. Okay, and these are the lower elements. So this is important because what we are doing here, remember that in Grasshopper, the way that values or data is sorted inside a list doesn't change unless you want it to change. So you must do something in order to change the way that data is ordered or sorted inside a list or a data structure. So what we did here was plug directly the primary lines to this curve container and straight inside this line-to-beam component. So the beams that are being generated by this component are basically following the same order as the primary lines here. So they are up, down, up, down, up, down, like this. Okay. So if I take the first element of this list, it's going to be this little element here, but the second one is going to be this one. So if I want to come up with a customized order of these elements, what I need to do is eventually rely on this further implementation that I did here using the dispatch component. So if I want to the beams to be created like in this order, first all the upper beam and then all the lower beams, then I must plug these two things inside this component here. Okay, so I can take this dispatch, and it doesn't change anything in terms of structural analysis, of course, because the elements are going to be exactly the same. But I'm connecting, in this case, only the upper elements. As you can see, the lower element disappeared. And now I'm going to shift plug also the other wire. So we are back exactly to the same result, but the order of our beams have changed. And now that I know this, I can also do another thing. I can give these elements here, these beams, an ID based on this order. So, for example, I can use something like the letter B to identify the beams. B dash and use a concatenate component just to generate names. Right? So I want these beams to have a specific ID. And the ID is going to be a char sequence, which is going to create something like A, B, C, D, E, F, G, H, I, or you can create a series as you please, if you want some letters or you want numbers. Okay? So in this case, what I need is an amount, a quantity of numbers, of values, that I'm going to plug in fragment B. Okay, so in order to have the final name of the beams. So if I do this, I'm obtaining B0, B1, B2, B3, and so on. If you want to avoid B0, which is something that unless you are a programmer or coder, you don't want this to happen. So eventually you can set start value to 1, and that's it. Okay, so this is the IDs that we are going to use for our beams, and we need as many IDs as the amount of beams that we have. And the amount of beams that we have is going to be defined by the length of these lists. So it's actually 28. Okay, this is something that you can, let's say, extrapolate from these two things here, or you just count the amount of values that you have here, or as you clearly know, you can also multiply this by 2 directly. Okay, so whatever method suits your workflow, you can use it. So in this case, what I'm going to do, I'm going to create a list length component, and I'm going to plug this and this together. Remember that when you do something like this, in order to avoid any type of error, I would flatten this just to be sure that no data tree is going to be calculated. Because if for some reason you get a data tree here, you will have two different systems in Caramba 3D that will be calculated at the same time. And so this is going to be finally 28, and this is going to be the amount of values that we need for the beams ID. And once we have these, see that now it is switching up to beam 28, we can plug this to the identifier of these. You can also, let's say, specify this ID with relation to the function that these elements have inside the truss. So eventually, instead of using simply a B, you can refer to the primary, brace, and vertical names. So this is going to be eventually primary. And we can do the same with the other elements, so in order to recognize them. But as we are going to apply the load only to the upper elements, we know that the upper elements are going to be, as we changed the order of the elements inside this input, then we only need the first 14 IDs that are coming out from this list of IDs. And these IDs, these 14 IDs, are going to be connected to the beam IDs where we want to apply the load. Okay, so in order for this load to work properly, if you don't provide an ID, the load will be applied to the whole system, and we don't want that. Okay, so if you want this to specify where you want to apply the linear load, in this case, you must give a name to the elements, and that name must be plugged also in the beam IDs. So what I'm going to do, I'm going to take this little part of the script here, and I'm going to do something like take this list length, and or I can, well, I can do many things as always in Grasshopper. I can also take a sub list where I take the list of names that I got here, and as a domain, I want to use this slider here. If I use this slider as it is, like plug 14 to this domain, the actual domain is going to be 0 to 14. And this is too much, because 0 to 14 means 15 values. Because remember that lists in Grasshopper begin with number 0. So 0 to 14 is not 14 elements, it's 15. So if I want to use this slider here, I must do something like a small math operation, like a subtraction, and subtract 1 to this. This subtraction here. I cannot do it as an expression in the domain input because this is not a numeric value. The domain is not a number, so you cannot apply an expression in this input. You must do it explicitly here before connecting this here. And so we are getting only the names that we need, the IDs that we need from P1 to P14. And so this is necessary in order to apply the load only to our upper beams. If everything is correct, we will see this when we will build the model, because Corambar 3D actually is capable of showing the loads, reactions, supports, and so on graphically inside the preview here. So we should see linear load applied only on top of this truss system. And the vector, of course. Okay, so vector, once again, this is actually exactly like in Millipede, as we saw yesterday. We need to specify an orientation, which can be whatever orientation you might want to use. We are going to use a vertical load, like something was lying on top of this truss, but you can use whatever direction you want. And I'm going to give this a negative expression. And I'm going to plug here a 101 slider. Always consider that what unit is this component using. For example, now is kilonewton and not newton. Yesterday we saw in Millipede, if I'm not wrong, that it was working with newton. Okay, so just pay attention to the magnitude that are at stake in these definitions. And the orientation. Well, actually, not the orientation of the load. The load is perfectly defined as regards the orientation, but the orientation according to the way that this load acts on these elements. For example, now these are horizontal beams, right? And this is a vertical oriented load. So the load acts like perpendicularly to the element. But what if you are applying a vertical load to a diagonal beam? So in this case, this orientation refers to how you want to, let's say, distribute this load along this line according to what orientation. So if you select the local to element, this load, even if it's vertical, will act perpendicularly to the element. But I would recommend that you use global. Okay, global allows you to use the global orientation of the vector that you are using, that you have specified here. Okay. So that's it, because we already have, and if you want, you can specify that this load belongs to a specific load case. So it's just a number. It's like an ID for a set of loads that you want to use. So you can specify different load cases, and then the same system, you can analyze the same system according to different load scenarios. Okay. So yep, that's pretty it with the load, and now we need to define the supports for this structure. So let me expand this a little. So we have the model support. Let's place it down here, and it's very similar to what we saw yesterday in Millipede. You have some switches that avoid XYZ translation and XYZ rotations. So in this case, you must specify the position of the support points. Well, here we could do several things. We can anchor this structure, for example, only at the bottom if we want to create some kind of truss beam. Or we can anchor all the four vertices, the four corners of this structure, or only the upper corner. You can do whatever you want, basically. And you can use also different type of supports, of course, like fixed support here, and here you just place a translation support. But anyway, let's keep it simple once again. I'm going to use some analysis from the original two curves. So I'm going to take the endpoints. These are the upper endpoints, and these are the lower endpoints. So let's say we anchor this structure to the four corner. So the position of our supports will be both start and end. Now, in this case, there is almost no risk that things here are not blending merging into one single list, because they come from the same process. But if you want to keep things clearer, you might also want to flatten the points before plugging them inside this support component. And of course, if you want different type of supports, you must use different instances of this in order to activate or deactivate respective translational or rotational constraint. So in this case, we must specify, for example, that we want this to constrain all possible degrees of freedom. And that's it. Once again, as we did yesterday, we have the geometric aspect, the supports, and the loads already defined. And we can move to building the model. So it's assemble model. Once again, we have this. It's like a concentrator of all the features that we have defined previously for the model. But in this case, it's everything is separated. You see that we have element, support, and load. These are the three main inputs that we must feed with values. Okay, it's not like the model, the FE model component in Millipede, where you plug all the elements inside one single input. Here you must specify them like separately. So our elements will go into the element input, like this, and there is another one, which is this one. Then we have the load, which is going to be plugged here, and supports are going to be plugged here. So you see that in this case, for example, there is also cross-section, material. You can also specify some joint. In the model definition, there is a, or am I wrong? No, in the cross-section maybe? Yeah, beam joints, for example. You can add hinge as at the endpoint of beams if you want. But anyway, you see, when you see here, for example, cross-section, we already defined the cross-section at the element level. Okay, so it's this one. If you want to override the cross-section that you have specified by element, you can plug here a cross-section, which is going to be used for the whole element. So it's like overriding properties, elements properties at the model level, and the same for the material. Okay? So if you don't specify these features at the element level, you can do this like in general, like globally when assembling the model. Okay. So that's it. This is actually creating the FE model, what was the FE model, and immediately it calculates the mass. Okay, so mass is not depending on the deformation. So that's why I was surprised when you told me that you had a negative mass in millipede, because actually, even if the weight is actually coming out from the solver in millipede, is actually a geometric property, a physical property of the original system. So you see, it's immediately available, and it doesn't change. Okay, so it's not a result of the simulation. So it's immediately available in Caramba 3D when you assemble the model. So this is something that, according to the workflow that we were adopting yesterday, this is something that we might want to immediately connect to a number container and give this a name, take a panel, give it a name, plug it here. And we are already preparing for the optimization processes. So this is going to be the first one. There is also another property, which is the center of gravity. This is something that eventually you might want to, it's a quick glimpse on the general distribution of masses inside your system. So we are working with a truss, but if this was a let's say, a more complex object, the viewing or analyzing the position of the center of gravity immediately gives you an idea if the structure is well balanced or not. Okay. And the model is this. It's just a summary of what you have inside. There is no actual, let's say, detailing inside this output. So it's not like with Millipede where you have a full list of elements, each one with its own properties. So it's just information that is prepared to be passed to the analysis. And there are several types of analysis that you can run in Caramba 3D, but even if they are named like in a more explicit way, there is something that you might recognize. For example, there is the vibration and eigenmodes that they were also present in Millipede. But anyway, let's stick to the simplest analysis that we can perform, which is the analyze Caramba 3D component. And you just plug the model here, and here it is. Now, this is actually giving us a warning. Oh, okay. Yeah, it's just warning that your system might be redundant, basically. But nevertheless, this is smart from the plugin because one of the objective of a structural engineer or whatever professional is actually dedicated to structural design, and optimization is one of the main factors. So in this case, this warning is not because there is some error or mistake in the Grasshopper definition. It's just that it's not an optimized system eventually. But nevertheless, we don't care about this. We are going to take this into account during the optimization process. So this is doing the calculation. You see that these components here, even if they all have the preview, if you turn on the preview of this component, you see nothing. In this case, only the center of gravity. Okay, so there is no geometrical preview for these things here. The first geometrical preview that you get is when you analyze with the model view, for example, the results of this simulation. So once you plug the calculated model, and by the way, you see that here we have the maximum displacement. It's already present at the analyze level, of course. And so if you want, we can also, let's say, immediately isolate this other optimization parameter here, like maximum displacement. Remember that this time it's in centimeters, so just pay attention to the magnitudes. You see that we only have 1.14 like maximum displacement. I'm going to make this like maximum displacement like this. And also here, max displacement. This name here is going to be used inside the optimization algorithm in Goldfish. And so we plug the model here, and here we have a full representation of what we are creating in our model. Okay, so let me go into perspective mode, and I want to, well, no, I don't want to turn off the preview of the original system. You can see, for example, that there is also a representation of the joints in this case. All of this preview here can be adjusted, can be customized. So there are many parameters, many tweakings that you can do inside this model view. See how many tabs it has. So display scales, for example, render settings, tags, if you want to show tags and labels of for your elements, colors, result case. So here at this level, for example, is you see that in this case you assemble the model and analyze the model, and there is no indication about the load case that you are using. So the load case is something that in this case, for example, you see that yes, it's just here this result case. You see that is by default it is set to -1, but here you can change, for example, what case you want to analyze in your system. Once you once you have this component running, you can customize the output. It's very useful if you want to produce some kind of technical drawings, for example. So you see deformation. Once again, this is like the representation of the deflection that we had in millipede. You can increase or decrease this as you please. It doesn't represent the actual deformation, of course. It's just to have an idea of what happens in your system. It's if you want to give this slider here a specific value, it's very difficult that you can do this by sliding this cursor, basically. So first of all, let's try to understand what's the meaning of this, for example, 34, right? So if I go in this preview, and it's easy to recognize that the maximum deformation is happening here at the center of the system, right? So if I go, for example, here, and I disable the grid snap, and I go and measure, for example, from this point to this point, you see that we are getting this. Now, it's not precise. I was clicking like, why their curves are double? They are not double. They are basically, it's the original system, the undeformed system, and the deformed version. So that's why you see these double lines. But if we turn off the preview of the original system, which are these three things here, you only see the deformed version of the system. So basically what we are getting here is that the distance between the original system and the deformed one in the point at the center where you have the maximum displacement is more or less 0.30 something, which is exactly the value that we are getting here. So if I double click on this slider control pops up. I can decide many things here. How much precise do I want this deformation to be variable? But I can also specify the value. And this value is basically a multiplier. So if I set this to 1 and hit OK, the deformation that I'm displaying in this system is actually the real deformation. Remember that the deformation was, the maximum displacement was 1.15 centimeters. And so if we go here and we go inside the display scales and deactivate the joints, you see that there is this small displacement here. This is the 1.14. So see, this is the actual deformation of the system. Okay, so leave deformation to 1. Avoid displaying like geometry or previews that are like covering the features that you want to analyze, and then you can simply see the results. But it's nice to have a better understanding of what's the behavior of the system. Like this is by default, this value is set to 50. So it's 50 times the actual deformation. Okay, so it's more or less 50 centimeters right now. You can also display forces and reactions. So if I click on reactions, now we start seeing what are the reactions at the support level. So these are the actual reactions values split into horizontal and vertical components or contribution at the support level. Normally, the length of this vector corresponds to exactly to the intensity of this, the magnitude of this force. But you can, once again, you have a scale factor here that you can reduce in order to have a more, let's say, human scale representation of these reactions. Okay, something like this. Then there are the loads. You can display them or not. And you see that we did things properly. We applied the loads only to the upper beams. And you see that these distributed linear loads appear only corresponding to the upper set of horizontal beams and not at the bottom. So yeah, we did things properly. And you can also scale them if you want to have a better or clearer representation of this aspect. Supports, you see these 4 symbols that you see here. You have a graphical representation of what movement or what translation or rotation are being constrained by the support with this symbol. So 3 arrows and 3 circles means that this is a fixed support. But for example, we can also, I don't know, change and allow horizontal displacement. So you see that the horizontal X arrow is no longer appearing in any of the 4 supports, okay, like this. And of course, the horizontal contribution of the reaction disappeared totally, also here at the top. So you only have vertical component here. So it's totally interactive. You can play with this, and you also have this kind of numeric information, which is so valuable. Local axis is actually indicating what's the orientation of the elements that form this system, and they can also be scaled up or down if you want to have a more clear representation. And the x-axis is normally the orientation of the linear element. And the joints, which is giving you an idea of how many elements are connected together into one joint. But it's just a graphic representation, so there is no rocket science here. And render settings. Render settings, you can basically, in this case, as we are working with just linear elements, this component here doesn't give you a representation of the thickness of the geometry. There's another component that we are going to use next that gives us a representation of the elements. But this is something that allows you to increase or decrease the resolution of the system, the deformed system. Okay? And there are tags. So if you want to recognize the elements that you are using in your system, then, for example, element IDs, we have our beams, P1, P2, P3, they are in order, of course. The other one, we didn't give a name, an ID, so there is no ID for the diagonal and vertical elements, just for the upper and lower beams. As well as the node tags. The nodes are tagged automatically. So this is important, for example, if you want to give some construction documentation, then you can easily identify at node number 22, etc., etc. Okay, so it's very interesting feature. Load values, if you want to have an idea of the intensity, the magnitude of the load that you are applying, so you can also visualize this here. Just for the resolution of the model of this representation also affects the intensity or the basically it's the amount of subdivisions that you have inside your linear elements. So we are basically creating 3 subdivisions per element in this case, or less if you want. Okay. So you can increase the density of the representation as much as you please. So let's go back to what? And what else? Well, if you want, you can also visualize cross-section names, material names. But anyway, normally the Karamba representation visualization becomes too crowded when you activate all these tags. So I would recommend that eventually you don't display anything, not even the load values, unless you actually need them. Okay, because else it becomes extremely crowded, and you don't read the behavior of the structure anymore. So just the essential. Eventually, if you want, you can also hide, for example, the reactions. So this is giving us the idea of what happens inside our system. Also, let's turn off the center of gravity. We don't need it. So this is the general behavior of our system. Now, of course, this system is subject to variation. The moment that we, for example, change some values inside our element definition, you see that we have more or less deformation, of course. And this is something that we want to eventually optimize. And the other thing that we can do is, after we have the general result of this simulation, we can go once again in result, and we can take the beam view, for example, which is a visualization component, like the ones that we had in Millipede, that were capable of showing the thickness of the elements, the geometry of the elements. So we take the model and plug it here. And so we have a actual physical representation of our elements. So in this case, for example, we can decide what we want to show, what we want to display. Like in Millipede, remember that the frame visualization allowed to visualize, for example, just the geometry, like the mesh preview, which is this one, by the way. Or you can change, for example, and visualize the stress or the forces involved at the beam level, at the element level. So for example, well, in this case, this is a truss. So moment X, moment Y, moment Z, they are all basically not. This is only a compression tension. So the end stress is actually producing some outcome. Okay. So these are the normal stresses inside these elements, so compression and tension. You can display them just like this floating line, which is absolutely useless, but you can also feel these areas. And so you know where there is compression or tension. Compression is red and tension is bluish. Of course, with this scale, you don't read anything, but if you decrease this value, then you have this behavior like represented at a more proper scale in order to understand what happens to these elements in your truss system. And if you want, you can display the numbers, but once again, if you display the numbers, you get this. Now, fortunately, these numbers are not fixed size. So if you zoom in, you will have a clearer idea of the values that you have at the element level. But if you want to, for example, print these at the truss scale, then you have this kind of unreadable graphics. So I would recommend that you don't populate your graphics here. And render settings allows to display different well, aspects of this structure. So I'm going to deactivate the normal stress, and you see that actually we are seeing the cross section, which is corresponding to the mesh representation in Millipede, but you can also display the axial stress. So you have the highest compression in red and the highest tension in blue purple. So it's and you see that you have another resolution control here. So this is actually increasing the amount of the resolution of the mesh that you are displaying. So you see that the only thing that increases is the amount of edges and faces of these polygons. And of course, in our case, these elements, they are truss beams, truss elements, so they cannot bend because we told them they cannot bend. They are truss element, and all of them. So there is basically no need for increasing the resolution because these elements are staying linear. So there is no need to increase the resolution, which is something useful when you want to have a better representation of the deflection or bending of a linear element. So in our case, there is absolutely no need to increase this. Also, we can decrease it to the minimum level, which is 1. And we can also represent the displacement, for example. So it's maximum here where you see this pinkish area or purple area here at the center, and white where you don't have displacement. Of course, this element is anchored at both the endpoints, so there is actually no displacement at all. And utilization, which is something which is interesting because this is what this component here is basically telling us. There are some elements in your system that are redundant. So for example, if you see that in terms of usage or utilization, this is actually white, this is white, you know. So actually this one, for example, and this one, we can simply get rid of them because they don't, well, work at all, okay? So that's what that orange component was telling us. There are elements that you can simply avoid in your structure because they are not being used during the simulation, or they don't contribute basically to the stability of your system. So this is actually this is what this parameter or visualization is telling us. There is also here, when you have this output, you can also use this thing for different purposes. So this visualization here can also be exported using meshes of rendered beams. This is actually these are actually mesh objects. So you can import them into a mesh container, and here they are with their own respective color. Okay, so you can also use them for any other workflows that you might want to adopt. And there are also the beam axes, which are this one. Oops, sorry. I think that the beam axes are, yeah, is here. Deform axis. So these curves are available for further analysis or workflows or implementation that you might want to use. Okay, so the difference between, for example, deformed mesh that you see here, you see that it is actually not displayed at all, is because we are not using a mesh model. We are using lines like elements. Okay, so there is no mesh at the model view level. It's just line. If you want a representation of these elements like beam with the mesh properties, then you must use a beam view. Okay, so that's why you don't have any output in deformed mesh. This is different when we will be using, for example, a shell structure, which is actually a mesh. Then you will already have a deformed mesh coming out from the model view because it is actually a mesh. Okay, so that's the difference. So this is more or less, this is what we need for now to try and run an optimization process on this element, on this truss. I'm going to also see this from the displacement point of view. But no, because the displacement is not going to change. Actually, this is a beam basically subject to a vertical load applied all over the extension of the beam. So this truss is going to deform always the same. So this is always going to be the more intense purple area. And this is always going to be the whitish area. Okay, so displacement is basically not relevant actually. So I'm just going to leave the cross-section visualization, like the mesh visualization of our model. What I want to do, I want to optimize this system. Okay, and in order to optimize the system, the only thing that I can do actually is play a little with the cross-section properties. And we have defined the cross-section properties by using a couple of sliders per element. Okay, but finally, what we are using here as lines, connection lines, are 28 lines for the horizontal, and then we have 14 lines for the diagonal, and then we have 15 lines for the vertical. Okay, so we need this amount of values for all the cross-section properties like height and upper width, lower width, that we are going to keep equal. Okay, so we need a couple of gene pools for each cross-section geometrical parameter, and these inputs here tell you, yeah, okay, this input here is telling you that the component applies the longest list principle with respect to the input lines. What does it mean? The longest list principle is the principle that Grasshopper uses by default when you have some data interaction inside the component. Okay, so this is something that we just used here in this concatenate component here. So we told this component you must concatenate this P minus with this list of numbers here. And the result is that P minus is being combined with each one of the elements that come into fragment P. So we get P minus 1, P minus 2, P minus 3, and so on. Okay. So what this thing is telling us is that if you provide one single cross-section, which we are doing right now, this cross-section will be applied to all the lines. So all the beams will share the same cross-section. But if you provide two cross-sections and you provide 28 beams, then the longest least principle works like the first cross-section will be applied to the first line, the second cross-section will be applied to the second line, and as there are more lines than cross-section, the last cross-section, meaning the second cross-section, will be applied to all the rest of the lines. So we'll have only one line having the first cross-section, and all the rest will share the second cross-section. So in order to have as many cross-section as elements, we must provide as many heights and widths as the amount of lines that we are converting into beams. And so the gene pool that we must provide for example, the height must contain, in this first case, must contain 28 values. Remember that these are centimeters, so if you want, you can also add decimals to these values. Eventually, we can add 1 decimal if you want to consider. Normally, when you go with a provider, the size of this kind of profiles is in millimeters because they are almost considered mechanical parts, in terms of the production processes. So you could eventually use 1 decimal in this values definition. Okay, so eventually I will leave this to 1, and the smallest height that we were considering was 10, and the highest, if I don't remember wrong, it was 40 or 50 or something like that. So between 10 and 40 centimeters with 1 decimal value. Okay, so 28 values. So if I do this, now here we already have longest least applied because we have 28 heights, but we have just 1 width for both the upper and lower parameter. And so we get 28 cross sections. And as we have 28 cross section and 28 lines, each line will receive a specific cross section. Now they are all the same because the sliders in the gene pool, they all are at 25. So that's why cross section is telling us that if you see trapezoid, height 25, constant for all. But if we take this and copy it and get rid of this other slider and plug this also in upper width and lower width, now everything is correct according also to the longest least method, because when we have 28 combined with 28 width values, then we will have 28 cross sections. Okay, so we have 28 cross sections and 28 lines and 28 identifiers. Okay, so each element here is receiving 1 ID, 1 cross section height, and 1 cross section width. Okay, and we must repeat this for all the elements that we have in our model. So let's collapse these 2 things a little, and what I'm going to do, I'm going to Control-C, Control-V them, and substitute. And of course, in this case, we must double check. We have only 14 lines, so we need here 14 and 14. The range is actually the same, so I'm going to get rid of these 2 sliders. The structure relaxed because there are some default values here, which is 10. So that's why the structure just falls a little lower. But I'm going to use these and go back to, well, I wouldn't say normal because it's actually 25. So they are going to be thicker than before. So the formation is going to decrease. And here also we have 15. So I'm going to take this and I'm going to get rid of them. And see how, for example, in this case, we are considering the vertical lines. See how changing the height and width of these elements didn't change the deformation too much. because you saw that most of the vertical elements were actually not used in the final stress analysis. So that's why nothing changed when I removed the sliders from height and width. But anyway, let's as one of the parameters that we are going to optimize is the weight, then eventually Goldfish will try to decrease the thickness of these elements, and they are 15. Remember that these components, they all work with the longest least method or principle, so you must provide the proper amount of cross-section, because now we have 14 cross-sections and we have 15 lines, so we will have two elements sharing the same cross-section, which is not correct in terms of the optimization. So this must be 15, and this must be 15 as well. And so, yeah, that's pretty it. So we have this thing, and we can also do another thing. And remember that we can select the truss toggle. So we can select, for example, this truss, or this one, or this one. So of course, this alters the, changes the deformation. You see that the beam falls a little more with the type 1 and type 2, which are basically equivalent in this situation because they are just symmetrical, while the first is producing actually less deformation, less deflection. Okay, but anyway, this is going to be also a parameter for our simulation, for our optimization process. So we are also going to find out what's the best truss system in order to bear this kind of load under this support condition. So we already have prepared the objectives here. So what I'm going to do, I'm going to grab Goldfish. The objectives, well, are the mass and the maximum displacement. And as for the parameter, I'm going to use the truss type, and I'm going to use the width, the height and width of the horizontal beams, and the height and width of the diagonals, and also the height and width of the vertical elements. And that's it, because load is load and we cannot play with it. Okay, so I'm going to, I don't want to see the numbers. Actually, it's something that we already can see it in inside Goldfish interface. So I'm going to open Goldfish and place this window here in order to see what happens inside the system. Remember also that it's a good thing to activate history in order to have an idea of how the simulation is evolving. So reset, pause, and start. So you see that initially you always get this random distribution of thicknesses in this case. You see that the truss type is also changing. The calculation is quite fast. You see you have, well, actually less than 1 second per configuration. So we already have an iteration. And at this point, you press the history button. So we will see what happens with this simulation. Remember that the optimum situation is when you see these dots concentrating more and more towards the lower left corner. Now this simulation should run quite some time. It takes some time because there are lots of possible configuration, of course, because we have lots of elements in this truss system. I think I already saved an image for this. I think, I'm not sure. No, I don't see it. I have said something about the shell analysis that we are going to create, but I don't see the. Oh, maybe I have it in my. No, who knows? But okay, so never mind. Let's see if the good thing with goldfish. Remember that you can pause the simulation. You can eventually see what happens when you reinstate this. Remember that we already have an idea of um, how this the final result should look like, because we already know that more used and stressed elements are here at the beginning and at the end of this truss system. So eventually is in this area is where we expect to have thicker elements. So this is something that the only indication that we can have from the visual analysis that we already did. See how the maximum displacement is actually dropping to less than 0.16. Remember that this is actually centimeters. So it's 0.2 centimeters here. So we are lower than that. This is actually 0.15. And now it is actually even less. Of course, we pay this with a heavier structure, 95,000 more or less. So if you let this run over and over, we are just at 6 iteration. It's fast, but not that fast as yesterday with Millipede. But one thing that you can do eventually, let me pause this. Okay, let me close it. And also let me do something like this. I don't want to, I want to deactivate this. So Control E. And leave only the model view active. So we have no rendered mesh right now. And remember that this is also part of the time-consuming processes. So rendering a mesh is always occupying the processor, the CPU for rendering something, or the GPU in this case. But anyway, it's something that makes Goldfish run slower. So eventually, if you turn off the preview of heavy object, in this case, the heavier object is the mesh or are the meshes. Eventually, it can run a little faster. Anyway, it's something like barely notice the difference. So you must let this run over and over, and you come up with some interesting. Oh yeah, I think I know where this thing is. So if I go, for example, here, I think I have it here. Yeah. So this is actually the representation of the usage, if I don't remember wrong. This is the usage, and this is also a diagram of the actual deformation that we have, the deflection that we have represented with a colored surface generated by the undeformed element and the deformed element. Okay, so this is the meaning of this. It has the, let's say that this thickness here is not related to any stress information or you know, some force analysis. This is just to represent the deflection that we have. So yeah, this is what we should expect. And also, I think I had also, no, I didn't save this image, but anyway. I did a study where I was using the actual thickness to create some organic shape for this truss system, but I didn't save it, so it was just in my mind. So I think we got already to less than 0.15 centimeters. You see that we still add dots in this area, even if we have this one. It's still adding dots in this area because these are more optimized because they are also optimizing the mass of the truss. Okay, so for example, let's pause this forever. Let's reactivate the mesh representation. Of course, this is somehow messy representation because I don't know at what iteration I stopped the optimization, but we can also, this is the last iteration. And it doesn't mean that you have better solution, right? It's a mix of better and worse solution. So that's why I do recommend that you activate the history, because you might notice that there are more solutions that are not visible in the last iteration, but that might be useful for us. So if we prefer to make this structure lighter, then eventually we must select the points, the dots that are here on the left. So if I select this, the structure weight, let me do this, is 74,000. Okay, Luis, wait a second. So if I want a lighter structure, so I will restate this. Um, as you see already, the vertical elements are thinner than the diagonal and horizontal one. This is something that we were expecting to happen. If we want a balance between the mass and deformation, you take the dots that are here in this middle or along the 45 diagonal. So this is actually producing this kind of result. You see that always the vertical elements are always thinner than the other. And then if you want to prefer the deformation, optimize the deformation, you take the bottom points here, bottom right. But of course, less deformation means thicker structure. So you have a heavier structure and therefore thicker elements. Okay, so in this case, this number of iteration is too small, so we need more in order for this optimization process to find a better solution for this system. Okay, but anyway, this is something that allows us to optimize also this truss type system. So Luis, how do you get the information out of the Grasshopper plugin for a presentation if you want to make a diagram? What information, Luis? Which one?
I don't know. Maybe if you want the displacement or something, if you want to make it a diagram for a presentation, how can you get this like in a PNG file or?
But you are talking about this?
No, I'm talking about the
This one?
Yeah, this one.
Oh, but this is just Rhino preview. Actually, since Rhino since Rhino 6, I guess, you are also able to define the resolution of the exportation. Once it was just like a print screen or something like that. But now when you right click on the viewport that you want to export and select capture to clipboard or directly to a file, so for example, let's say a file, you are allowed to select also not only the aspect ratio, but also the resolution. So actually the viewport measures like 1920 by 114, but you can scale this up or down if you want. So the actual export should be more or less 4K image. So if I do this and hit OK, I'm asked to, well, where do you want to save this? It's going to our folder. I'm going to save it like a test. So it's going to be 11 GHP export image test.
So this is the way that you do to make the image that you showed before?
Yep.
Okay.
Yep. And of course, in that case, maybe, well, no, actually, yeah, it's exactly the way that I export those images. So can you get a moment and share diagrams values? Yes. Yes, exactly. That's what I did to produce that kind of images. So in that case, for example, coloring was obtained by using some custom preview component. So you give the color here and the geometry that you want to display with a specific color. You plug it into the geometry. So in that case, maybe I think this is already implemented here. Yes, it is. So if you want to take a look at the original script that I did, which was simpler because there was not all of these parameter here. But if I turn on this one, Control E, this is the standard system. There is also gravity in this case, like an external load, which gives its contribution to the system. But in the end, what I did here was exactly create the loft surface between the undeformed and the deformed system, and give some color to these surfaces. And so once you have this thing here, you just export it like I already showed you. And so it's the interesting thing is that now you can decide what's the resolution of your image. So you can also prepare an image for printing once it was with the resolution of the screen, which is too low for printing on paper. Okay, so here, so here we have the, let me go back to Caramba 3D, Caramba 3D tab. So we have the results. In the results, there are basically three groups of commands, three groups of functions. The first group is actually more graphic. The second one is analytical. And the third one refers to shells. So we cannot use it right now because it has no meaning, but we will be using this with the shell analysis. But if you refer to the second group, you will see that there are beam forces, beam resultant forces. So if you take one of these and you take, well, actually pay attention only to one thing. You see that there are, actually we are using the assembled model, analyze, model view, and beam view, okay? Each of them has a model output, you see? So pay attention to which one you use when you want to display, for example, the results. It's useless, of course, to use the assembled model because this is not yet an analyzed model. So when you see here analyzed model, refer to the analyzed component, okay? So this calculated model, you see that it's basically the output is more or less the same if you read it, but this already contains the information about the simulation that Caramba has made. So if you plug this into analyzed model, what you get here as a result are normal force, shear force, and bending moments. And here, if you hover with the mouse, you see that these are numbers. You see the 0.1 icon. Okay. So if we grab a panel here, we get normal forces in kilonewton, like in a numeric list of values. Of course, compression, tension, and so on. This is something that we already saw graphically inside this representation here. Okay, with eventually numbers. So we should recognize the same number here. 40605 is this one, and so on, of course. So you must use another, let's say, results component, but this time analytical results. Okay, and here you can, well, if you want to export this, you might want to write this information down in a file. The easiest way is to write this down in a TXT file, because you can use simply the panel. There is no need to do anything else. The important thing is that these values are organized in a data tree structure, as you can see. So each branch represents an element, of course. And these are endpoint and start point. You can specify here the stream destination. So it's going to be like here, it's going to be 2020, it's going to be GHA, and I'm going to tell this is going to be 200711 GHA, and what was this? I think it's normal. Yeah, normal force. Normal force results. And this is going to be a TXT, CSV, or whatever type you want. Of course, you don't use XYZ file because you are not exporting points in this case, but just choose the proper file type. I would recommend TXT or CSV eventually in this case. And so you just select the stream destination, and then you activate the stream contents. So you see that now it is activated, and this updates in real time. So each time you change something, if we go back here, we have the normal false results. Let's open this. And you see that here we have the values. Of course, the panel is not capable of let's say, exporting the data structure. And eventually the CSV is not capable of understanding a data structure, so you cannot pretend that you have this kind of organization of your values inside the Excel spreadsheet, but you can format your text before exporting it. And it's interesting here to see, for example, that we have 0, 0, 0, 0. All these 0 means that we have no stress, no normal stress inside a tension compression structure, so they are useless elements, basically. Can we create joints, heat, and assemble it, and further get analysis from the same along with beams? Yes, you can. As I showed you, you can also consider the joints inside your simulation. But we actually, guys, the thing is that we have so many things to see. If you want to go into details and you want to go into details with me, I think I suggest we organize something more like an additional class or something. Additional session, because I'm afraid we are not going to complete the program that I have in my mind. I prefer to move on with the program than adding more features to this. But yes, of course, Caramba. I think Caramba 3D is actually the most complete structural analysis plugin in Grasshopper. Which leads me to another observation, which regards Peregrine. They are both industry-oriented. So I would say that if you use Caramba 3D in your workflow, you are concentrating more on performance and numeric analysis in this case. If you use Peregrine, Peregrine is more about optimization, but a type of optimization that is suitable for the industry, for production. Actually, Peregrine is sponsored by Arup, as I was saying, so it is used actually by Arup to optimize structures. So it's another approach with respect to Caramba 3D, but nevertheless, they are both extremely valid software. I would recommend that you give them a good look in order to understand them deeply. But yes, of course, you can simulate whatever type of elements, including joints. The other thing that you can do, just completing the answer, is that you could also export directly to Excel. There are some plugins that allow Excel file write and read. Well, as you can see, this is somehow something that you can find in several plugins. Let me take Excel write, Control Alt, and this is from Launchbox, as you can see. But there are other plugins that you can use for this in order to have a more organized export of these values. Okay. So you're welcome. So that's pretty it for this simulation. The next one is going to be probably the core simulation of this workshop. Is going to be this one, where we will be using both Millipede and Kangaroo to simulate and optimize a catenary structure. So we will be creating a catenary structure at first, which is the easiest part, and then we are going to implement two different strategies to optimize this structure. And we are also deriving from this, in order to have a glimpse of what follows, we are also going to create a shell optimization process both in Caramba 3D and Millipede, in order to see how they works. And then we are going to deal with 2D and 3D topological optimization. And in this case, we are going to create 2D topological optimization with millipede and 3D topological optimization with millipede and with topos. I wanted to show you also the alternative to millipede, which is discontinued, as I told you. So topos should be the actual alternative to millipede for 3D topological optimization. So, yep, so that's pretty it. I'm going to just organize this thing with I would use a jump right here in order to remember that these two things are basically connected. And yeah, okay. So yes, the last thing that I wanted to show you about this this simulation is that once you have the optimized system that you can analyze in several ways. So this is actually oh yeah, this is the utilization of elements is another result output. So if I go back to Caramba, you see that results, there is also a utilization of elements. And in a truss structure, it's quite important because, and this is also giving you numeric values. Okay, so you have maximum tension, so sigma, tau, and you have utilization in terms of normal stress and shear and moments and so on. So I was using this to optimize this truss. Because what I wanted to show you is that when you have a multi-objective optimization algorithm like with the one used by Goldfish, you can also, let's say, create a multi-objective with more than two objectives. So in this case, for example, there is the usual mass and maximum displacement, but I am also trying to optimize the normal stress utilization. Okay. Why? Because if I optimize this, what I'm saying is that I'm creating a more even distribution, for example, of the stresses inside the structure or whatever type of consequences I want to implement in my system. So let me also, and I am also visualizing this with this. Okay, so actually these colors here, I was wrong. They are not representing the displacement. They are representing the usage, the utilization of the elements, and of course the area or the displacement here is actually the actual displacement of the deformed system. But the values, the colors, are not correspondent to the displacement. Okay, so this is the usage. The more used elements are the reddish one. The white one are basically not used in terms of normal stresses. So this is actually the information that we get from this graphic. And if we run, in this case, Goldfish, you see that as choices, you have three different choices. You can optimize displacement versus mass, displacement versus utilization, and mass versus utilization. You see that Goldfish stores this information also when you, this is something that I ran, I think, a couple of days ago before starting the workshop. And you see that this information is still stored inside the Goldfish component, even if I close the file and reopen it and saved it again, but you see that the information is still stored here. Also, yeah, I think that with history, I think I deleted everything. Well, sorry about that. But anyway, it's a very simple definition. So if I reset, pause, and start again, you see that the system is changing. The area here is basically the displacement. But if you want to see the mass versus utilization, for example, after one iteration, we already see what's the distribution. It's interesting in this case because we have this kind of phenomenon that I was describing yesterday. And the distribution of the solution in this case is like this hyperbola. And this means that the problem is very simple because if you decrease the mass, you have more utilization for the elements. If you increase the mass, you have less utilization for the elements. So this is something like intuitive. Also displacement versus mass. Okay, displacement versus utilization, it's a little more, well, the graphic changes, but the interpretation is more or less the same. So you see that there is a linear relationship between the utilization of the elements and the displacement. Okay. So yes, you can run a multi-objective optimization according to several parameters, but you can only consider them 2 at a time. Okay, so you cannot use them 3 for the same optimization. Okay, so this is the only limitation that we have here inside this goldfish analysis.